Alright, time for another draftphysics.com. Debatephysics.com also. Video presentation. So we're going to make another elemental argument for which we are begging the internet physicists to please counter. Please explain where I have made an error in anything I'm going to say in this argument. And it basically involves the simple real controversy that there's two ways to look at energy. Okay, physics has this kinetic energy formula. Okay, this that they say means something, that it's something to do with reality. And this is, for hundreds of years anyway, people sort of got the idea that it was just about mass and velocity, and they have a proportional, equal effect on how much energy something can impose on you. So make something twice as heavy, it'll apply twice the force or twice the weight or twice the pressure, and make it go twice as fast, and it'll do the same thing. So any increase in either the mass or the velocity increases the momentum because it's multiplied. And then this other theory, this alternative theory, was just proposed. It was never shown to be true with any physical evidence. It was just stated, okay, that somehow force or velocity has something to do with distance alone, and nothing to do with the force actually applying the velocity. So this goes back to an experiment that they've never conducted. They just tell us what the results are going to be. So they basically say if you drop something 4 times the distance, okay, it will have 4 times the energy. Now, even though they know, okay, that it's on Earth, it's 9.8 meters per 1 second of acceleration, and that the truth is this will only take twice the time, and it'll only end up being twice the velocity. So you're dropping the one thing, it ends up with 9.8. In 1 second, it'll travel 4.9, so it's always the same that way. And so this experiment up here is essentially exactly the same as this experiment. And what they're saying is that this is 3 units of energy. Even though you only increased the velocity, doubled it, added another 9.8, and you could understand that the velocity you got from the first fall, the 9.8 in velocity here, this is all for free right here. You didn't have to do anything. No gravity had to be imposed. The object was already moving, 9.8. If there was no gravity giving it a boost, it would just keep going 9.8. So obviously it would do the 4 units, the 2 units of 4.9. And all the new second did. The second, it just added this. And so all you ended up with is a velocity in the end of 19.6, twice the velocity, and frankly it's only twice the weight when you hit the ground, blah blah. And so they're basically saying if I took 4 pounds and dropped it this 1 unit of distance, it would equal 1 pound drop 4 units of distance. But 1 pound drop 4 units of distance is only doubling okay, the weight or pressure of the 1 pound, so it's short. Okay, it's only half the energy. So that's their axiom. They say it's true. There's no evidence that this is equal. Okay, that 4 going 1 velocity is the same as 1 going 2 velocity. These both equations apply. You can understand that, yes, because they're squaring the velocity, they can get away with this. But the simple truth is, momentum says, okay, it's no way the two can be equal. And the lever says they can't be. And again, they haven't done any experiment. So there's 0 experiment I can show you. But the truth is, logically, you can understand this in a lot of different ways. So a parallel experiment that I've mentioned quite a few times, and it just dramatically shows, it proves the point, in my opinion, kind of decisively. And you're just saying, okay, let's see if a physicist can say this isn't how it really works. So let's just say you had a height, and you were going to launch something off that height. all the physicists will recognize that the amount of velocity, all right, if I go twice the velocity, I'll go twice the distance, okay, so before I fall. And the faster and faster I go, okay, it's the same exact amount of time. So no matter where I go out here with faster and faster velocities, all of these arcs will be in exactly the same amount of time. So it'll take the same time for it to fall straight down as it'll take no matter what velocity I give it, linear velocity. So you can just look at that chart and you could sort of understand that if I was to draw a line in any arbitrary location, that each one will have a different amount of arc, okay, that's being covered, in the sense that it's going to fall at a different angle, okay, indicating less of the velocity is down and more of it is horizontal, okay, so that's the easy part. But the tricky part is to understand that in this amount of space, okay, you did this much down. So if I just make the arrows are all the same amount of down for each one of the cases, they all fell the same distance. So it's the same pressure, and you can understand that that pressure, in this case, all of it would have to be applied in this short distance. And in this case, all of it would be applied over this much larger distance, and then all of it over this much larger distance. So in each one of those cases, the lines, okay, of actual pressure per inch, okay, the pressure per inch for the shortest distance is the same amount of time. So you can understand this longer distance, okay, for the next one, and then for the next one it's even a longer distance with the same pressure. So they're all getting the same weight over a much larger surface. So per unit of surface, it's a lot less pressure. And so you can understand that you should be able to understand, okay, that friction isn't really a counter force. There's nothing that counters your motion. You're merely giving your motion to another surface. So if I was to roll a ball or to do anything across some kind of surface and consume its energy, so it starts with all the energy here, and by the time it gets here, it has zero. So it's going to lose all of its motion. And the simple understanding is the motion has to go somewhere. So we're just going to ignore the fact that it's going to move some air. Okay, so we'll just pretend, okay, forget the air, let's do it in a vacuum. And so the only thing that's going to be able to take the energy away is essentially the rubbing on the surface. And you could sort of understand that if I was to do the experiment by dropping a ball next to a wall, okay, that I'd have to blow wind, or I'd have to do something to push the ball into the surface for the surface to slow the ball down. But that any contact with the wall, you'd understand that any contact is going to take the energy away from the falling ball, and it'll take longer to fall because the contact is going to absorb the velocity. It's going to take some of its momentum. And the same is true in the rolling case. You can sit there and just say each bit of surface, okay, takes energy. And the point is how much pressure are you applying to the ball to take the energy. There's nothing else that can take it. The only way you can take all the energy into the surface is for you to hit the ball with a very firm force, and then it won't move at all because you've pushed it into the surface. So that's the argument, is that it really depends on how much pressure you're applying. Now, you know that gravity is a constant pressure, so it's 9.8 meters per second. So it can only happen in these units of time. And then you can figure out that, well, the units of time aren't going to be even because the velocity is not going to be even. Okay, the velocity is going to decline incrementally as it's moving. And you could sort of logically understand when it's fast, it goes more distance. And then when it slows down, it goes less distance. All right, and that's the reality. So if you were to measure the time, you'd find that this was 3 units of time, and that this was 1 unit of time, and that it was going half the speed here. 3/4 of the distance. So as units of distance, all right. So I'll redraw that. But you can just make direct comparisons. You could just roll something at twice the speed, and the fact is it'll go 4 times the distance because, frankly, it's not going to get proportional, or it's not going to be linearly equal, the amount of pressure per inch, because this entire part will just be 1 unit of time. So it's just all the gravity, all the weight of this ball can only apply that weight, and it has to apply it over this whole surface. So it's as simple as just like spreading peanut butter on a piece of bread. The bigger the bread, the thinner the peanut butter. And it's the same argument kind of here. So yes, it'll travel 3 times the distance, but it's only going to put the same movement here. So the momentum in the surface, that is the transfer of the momentum from here to the surface, there'll be just as much momentum in this giant area as there will be in this area, because it's the same amount of pressure being applied by gravity. It's a unit of time, and it's frankly, force is going to be only relevant based on how long you apply a force. That'll decide how much total capacity to move you has been applied. So I'll redraw this. Alright, so let's imagine, trying to imagine anyway, different ways of taking the energy out of a system. So let's say I just had 2 things that stood up and they were on a pivot so they could move sideways. So I could give them momentum in this direction. Okay, they can swing on a pivot. And I just roll a ball through, okay, that actually can't get through, so it has to hit them. Alright, so it's rolling and it's going to hit at some point on those 2 sticks. Alright, and it will be able to give them momentum. So it's going to lose its energy by converting it into the motion of the sticks. So the mass of the sticks will move in a direction, and obviously the faster the sticks move, the more momentum they took. The slower they move, the less momentum they took from the object. And that's all that's going to happen. Basically, you're just going to transfer the energy. The motion of this object will just be absorbed by each one of these impacts, taking the energy away, exchanging it. You're just going to move it like you move electricity from a battery to some other battery. You could recharge a battery with a battery. You're just going to move the energy from one place to another, and that's all you're doing here. And you're just saying, let's, for the purpose of logic and reasoning, just point out that there's no real losses except for this. We're not going to worry about air and different things. And sounds and whatnot, because it's a tiny fraction of the energy anyway. And the point is just to illustrate that this mechanism would be linear, in the sense that as long as you hit the same place on these sticks. But you could understand, okay, that if I change the experiment and say, well, the faster you're going, the less deep you hit the sticks. Okay, so there's a difference in where you're hitting. So if you're going slow, you hit the sticks here in the middle, and if you're going fast, you just hit them here on the top. Alright, now you have a completely non-linear, okay, outcome, because you're going to be hitting the sticks lower, giving the whole stick more velocity. So you can understand that if I hit the stick down here like a lever, this part of the stick will be going twice the velocity. So it's as if I'm putting twice as much energy into the sticks. It's not as if, it actually physically is. The stick will move faster, because the point at which I gave it momentum, the exchange, say if I was going 10 miles an hour, well, giving this part of the stick 10 miles an hour is a big difference than giving this part of the stick 10 miles an hour. The lower on the lever I push the 10 miles an hour, I'll be doubling the amount of, at half the distance, there'll be twice as much energy the stick will collect. And so the argument pretty much simply is the faster you're going across a surface, the less you're pushing into the friction sticks. So the idea is just to understand friction is just these sticks. You're going to roll on a surface, and the contact you have with the surface is dependent on how much weight you can apply to the surface, how much gravity pushes you into the surface. Without gravity pushing you into the surface, there's no contact with the surface, literally. You need something to push you into a surface. You don't automatically push into the earth. You're only pushed into the earth because of gravity. If you were in space and there was no, the body you were connecting to was not a significant weight, and there was no gravitational attraction, and let's just take charge out of it, you could go right next to the surface, and there's no way for you to hit any of the sticks because nothing's pushing you into the sticks. So the deeper you get pushed into the surface, the more contact there is, okay, and the more quickly you're going to lose your energy to the surface. And the less you're pushed in, the less contact, the less energy you're going to put into the surface. Alright, so what physics teaches, okay, is that I could have this example of just rolling two balls, okay, and one of them, I'm just going to, the only difference, they have the same mass, and all I'm going to do is give one of them twice the velocity. And the experimental fact is, this one will end up before it stops, and stopping means it's lost all of its energy to friction. Why is that glare there? That is weird. See if I can get rid of it. Oh yeah, it's from over here. Interesting. Yeah, you can see it now. That's a really interesting optical illusion, isn't it? I can make the text disappear. Anyway, it's just sort of annoying is what that is. Maybe I could adjust the camera. No, that didn't fix it. Can't turn the light off. Maybe I can turn another light on. Maybe that'll work. No, it really needs the shadow. The shadow knows. Yeah, so it's just a little too much light. Yeah, well, I'll have to think about that. Yeah, I'll just leave my hand up here. Okay. Well, it's another science experiment anyway. Alright, so what you can deduce is, okay, so this is just going twice the velocity. That's all I've changed. Now, yeah, you could fool a kid, and that's the whole point. If you're a physicist, you graduate from college. Do you think you should fool children into believing that this is 4 times the energy when 4 times the distance doesn't mean 4 times the energy, because you can know better. And you do know better, I think. I mean, I think you do understand that it is about how much pressure you're applying to the surface. So again, you know that this experiment here, so whatever this is, that's how long. When it's going one velocity, you know what it looks like. So one velocity does this little bit of distance. So you know it's going one velocity here because this experiment will be identical to this experiment. And so right there, that's telling you something, right? Half the speed here. It's going 1v here, 3/4 of the way down the track. Now, do you really think, that somehow it has this weird thing that half the velocity means that, the velocity isn't in equal chunks or something, or that the momentum isn't in equal chunks? I mean, how can you explain that defect where half the velocity isn't in the center where it should be if it was a linear experiment? It should be here in the center, not here. So obviously that's telling you something's not fair in how this thing is traveling. And the easy argument, again, you know that this is the same pressure or weight. So the same weight is being applied over this surface, right, that is being applied here. So if you were to measure their weights, that is, let them roll across these distances at these velocities, you know that these will measure the same weight. It's the same total amount of physical weight, okay, over this large area that was applied to this small area. So you can understand if you did that on ice, that if you put all the weight in one little place, the ice breaks. If you can get the weight spread over a large area, the ice doesn't break. Same kind of argument here. you're taking a force and applying it over a large area, all right, and at a less for each inch. But it's the same total force, so it's the same time. 1 second for this, let's just say it'd be 1 second for this, and 1 unit of time for this. So you know that it's all the same amount of time in the force that's applying the pressure. And because it's gravity, you know it's 9.8 meters per 1 second. So it can't be anything else but the same amount of force over this huge area that there was over this tiny area. And the same amount of force over this 1 second that was applied over this 1 second. So can you understand that it was pushed less into the surface? It wasn't as deep into the surface here because of the higher velocity. The higher velocity prevented it from being deeper because it couldn't put enough pressure to get in deeper, to make better contact, to lose more energy. So the bottom line is, I think a physicist knows the amount of heat or movement, okay, or heat's probably a better concept, so I should just say heat. You know it's going to be converted into, interesting, okay, that depends about had it. You know the amount of heat here in this surface is going to be the same as the amount of heat here. Alright, so I don't think anybody who graduated from college physics can't understand conceptually that's going to be an absolute truth. And it's just going to be 1 unit of heat here and 1 unit of heat here, meaning that it's really only 2 units, and it's only 2 units of real energy. That the energy dissipated here is exactly the same as the energy dissipated here, and it's only twice the energy of the one velocity object. It's not 4 times its energy. So the fact that it rolled 4 times the distance is a deception, plainly, if you don't understand the physics and understand that this moved down the same amount over this huge distance. You know, it went in a downward direction, pressure, the same amount. It didn't go deeper. It went the same amount as it did for the other thing, if you want to think of it in those terms. It can't lose more momentum because it's applying less pressure per inch. Can't really say it better than that, I don't think. It's less pressure per inch, per centimeter, per millimeter, per whatever you're measuring in. Alright, so the simple truth is this isn't a complicated puzzle. It's not a trick. You know, it's not a big complicated word problem. It's none of those things. It's just this simple understanding. It's a constant force. You can only get this much per 1 second. So understand, the further I let this go, the more outrageously crazy their statement gets about the energy it has. So with 2 seconds, it's 4 times the energy. 3 seconds, it's 9 times the energy. 4 seconds, it's 16 times the energy. 5 seconds, 25 times the energy. So again, and we know, like I said, you know this whole part here required no added energy. You got that distance for free, that velocity. You didn't have to earn it. You already paid for it right here. You got it for having your 1 second. And your second just gave you another unit of velocity. So you only have 19.6 again. 2 units of velocity. And that's it. You can't have 4 times the energy because you only went 2 units of distance, 2 units of time, and 2 units of velocity is all you have. There's no place you could have acquired the 4. Alright. Because the distance isn't how you're acquiring it. You're acquiring it in units of time. Time. Units of 1 second. If I change the 1 second to a half second, then I have to change the 9.8 to 4.9. I have to change this number if I change that number. So it's always in equal units of time. And in 1 unit of time, this is all you get. Same as this. So again, it's the same exact argument. The first second, this is what you get. And that's it. And this whole distance here, you're just getting the same thing. 1 unit of acceleration. Just 1, not 3. So there's no place you could have acquired the 3 units of energy. You only acquired 1. Really, it's just this isn't that complicated, and I just don't. I think it's bad form on your part to defend nonsense and garbage. And it's nonsense and garbage to defend 1/2 mv squared. It never does any real work in the universe. In cases like the gun and the bullet, it clearly demonstrates it violates Newton's third law. The kinetic energies are so outrageously different. And their argument basically is that if I could tie the bullet to the recoil of the gun, their claim is that let's call the bullet 1 atom. The 1 atom going 1,000 miles an hour will somehow, with 1,000 times more energy, 1,000 times more force, it will take the 1,000 atoms going 1 mile an hour that way and move them all that way with 1,000 times more energy. You can't really believe that's true. Can you? Can you really believe that's true? Or do you understand that, yes, yes, it's 1,000 atoms going a much slower velocity, but it's 1,000 atoms. All right, it's a lot of atoms, all right, and it's really the same energy. And if I could literally tie them to a tug-of-war rope, the recoiling gun and the bullet is going to be a tie. The bullet doesn't have 1,000 times the energy. It doesn't have 500 times the energy. It doesn't have 200 times the energy. It doesn't have twice the energy. It doesn't have any more capacity to do work than the recoiling gun. The same capacity to move matter. And the only thing the bullet has an advantage in is that it can apply its force over a shorter period of time and break things, because the things can't absorb the energy in the time that the bullet's applying the energy. So it can make things look like more energy, but you can understand it's really not more energy. A crack in a glass, okay? Yeah, the whole glass falls apart because of gravity or even air pressure. But you can understand the crack didn't take that much work. There wasn't that much energy to crack the glass. And you just understand that its form falls apart because of a lot of other factors. The simple argument is if I take a gun, a heavy mass, and I throw it at a piece of porcelain, or I shoot the porcelain with a bullet, I'm not going to change how much total mass I move. It's not going to be any different. If I take an 8-pound bowling ball going 16 miles an hour and I throw it at pins, and then I take a 16-pound ball going, take an 8-pound going 16, and then I take a 16-pound ball and throw it at 8 miles an hour, all the balls can do is transfer their momentum. So they both have the same momentum, and that's all they can give the pins. They can't give the pins more momentum or less momentum. So because the momentum has to be conserved, the kinetic energy is impotent. It doesn't mean anything, because the only thing you can transfer is the momentum. That statement alone should be enough to end the argument. And the fact that it persists and persists when there's no physical evidence supporting it, and they haven't done any of these elemental experiments, didn't do any tug-of-wars, no crash cars, no effort, no thermometers measuring heat, no effort whatsoever to validate this theory. Really. It's just a religion. It's just a Holy Ghost right in the middle of their physics. A piece of absolute made-up nonsense that never gets a right answer. And they put it right in the middle of their physics. Too stupid. And it's bad on you, really. Bad on them for lying to you, but bad on you for falling for it. Really? All right, just one more time. So in the rolling ball experiment, can we find a single physicist who will assert, with his reputation at stake, that we know the ball loses its energy to the ground? So is that an accepted fact? And as long as that's the accepted fact, we can start with that. I mean, if you don't believe that, you're also showing you don't know anything about physics. The only way this energy of these two objects can disappear, their motion, is they had to give it to the ground. So as long as we understand that's where it is. And if you're going to claim that this ground is 4 times hotter, all right, 4 times more active, I'd say it's heat, but I'll just use the word active, than this ground, when the simple answer is 2 velocity. Okay, and the simple answer is no. It's only twice as hot. And that's all. Twice the jiggle in this entire surface than there is in that surface. Only twice the energy was extracted because only twice the energy existed. Yeah, that's enough. Alright, so till the next time and such and so forth and whatnot. I really shouldn't have to keep making these arguments. I mean, really, you're proving, just how dumb the average college graduate is. You're proving it. I mean, people not watching this video aren't people, who watch The Simpsons and do all that sports and all that other moron shit. Okay? I mean, these are people interested in the subject of science. And you can't understand this simple argument and understand that it's quite decisive and complete. That you do actually know it isn't 4 times the energy in the ground. You do know that. Come on. You can figure it out. So quit playing the game. Just admit the truth. This isn't science. This was pseudoscience. It was just a statement made, and it was never backed up by evidence. And in 350 years, nobody cared to back it up by doing any experiments demonstrating it to be true. Ever. There's nothing. I can't show you an experiment because none exist. That's not science.